In this video, we're going to talk about forces at angles. Remember, whenever you have a force at an angle, you are going to find its x and its y components by making a right triangle and taking a look at which side is adjacent and which side is opposite. Typically, the x component, or the horizontal component, will be adjacent, so we use cosine, and the opposite is sine. We use these in problems where we want to take a look at what are the x components of all the forces. We used to do that with like a chart of x and y, and then we would label all the different forces, etc. And then we would get to a place where we would write what do the y components equal and what do the x components equal. And we're going to do a similar thing now, except we know a lot more about force and things like balanced and unbalanced forces and accelerations. So let's do a problem that's going to have a bunch of these forces with one of them at an angle. A box of mass m equals 2.4 kilograms is pulled across a rough surface by an applied force of 20 newtons at an angle of 37 degrees above the horizontal as shown below. The coefficient of kinetic friction between the surface and the box is 0.4. What is the acceleration of the box? Okay, so first of all, we're given some information that we should probably write down just so that we can see it clearly. We know the mass is 2.4. The applied force is 20 newtons at an angle, so we'll call that theta, 37 degrees. And it gives me the coefficient of kinetic friction, which I'm going to call mu k, and it is 0.4. Okay, next, I could draw the forces on this box, but now that we have so many forces, and I'm going to turn this applied force into a cosine and a sine component, it probably is a better idea for me to just draw a dot representing the center of the box, and then draw my free body diagram directly on that dot. So let's start with the applied force, F. I can go ahead and take this force and turn it into a horizontal or a rightward facing force and a vertical or an upward facing force. Now, these are going to be my x and y components of force, and this one is adjacent to the angle, so it'll be f cosine theta. This is opposite, so it'll be f sine theta. Remember, f is like the hypotenuse of this right triangle. Okay, so that's the first force. And then I'm going to figure out, well, what else is acting on the object? I know there's a weight force down. And go ahead and draw your weight force a little bit bigger. There's a reason for that we'll talk about in a second. And there's going to be some friction acting to the left, which we would call Fk. And then, of course, the normal force. Now, here's where things get a little weird. Normally, the normal force is just equal to the weight, unless the object is on like an elevator or something like that. Well, in this case, we have a new situation where the normal force is not going to be equal to the weight. And that's because when you are lifting up on this box at an angle, part of your lift is reducing the amount of force that the table or the surface, the ground, has to support with. So how do we figure out what the normal force is? Well, I know that it's going to point up. I'm going to draw the normal force up. And remember that when we look at the y forces, so I'm going to write this up here, sigma f y. When we sum all of the y forces in this problem, they're going to be balanced, meaning this box is not accelerating up, accelerating down. It's accelerating to the right. So I know that all the y forces are going to be equal to 0. Now, that means a couple of different things. First of all, it tells me that the arrows that point up are going to be equal to the arrows that point down. Now, I could do this a couple of ways. One is I could think, all right, well, let's just write out the net of these forces. Anything that points up is positive, anything that points down is negative. Okay, so normal force is positive. F sine theta is positive, they both point up, and the weight is negative, so minus mg. Okay, well, I know that these are going to equal 0. So what I can do is I can say the normal force plus F sine theta minus mg equals 0. Or I can quickly get to this equation by thinking about the fact that I just know that all of the forces pointing up have to add up to the amount of force pointing down. So I could probably just really quickly think, all right, n plus F sine theta, those are the ones that point up, they have to be equal to the weight, mg. Now, these two equations, they're equal. All I do is add mg to both sides. So we can just kind of quickly arrive at this equation without even thinking about net force, the sigma f, and the y components, and just sort of playing this game where we think about the forces that point up are going to add up to the forces that point down in this problem. And I know that that's true because the upward and the downward forces are going to be balanced. Otherwise, we would see the box accelerate up or accelerate down. Okay, so in the next problem, we won't go through that whole process. We'll just start here, where we have an equation with all of the y, or the up and down forces. So back to the question at hand. Well, what are we doing with this? What are we trying to do? We're trying to figure out what's the normal force. Well, to figure that out, I'm going to subtract F sine theta from both sides. So normal force is equal to mg minus F sine theta. Now, the reason why that makes sense is because in this problem, you are pulling up on the box, so therefore the support, or the normal force, is going to be less than the weight of the object because you're pulling up. You're pulling the weight up, so not all of it has to get supported. All right, let's put a number to this real quick just to make things kind of easy for ourselves. The mass is 2.4 kilograms times, we'll use 10 meters per second squared. And then F sine theta is 20 newtons times sine of 37 degrees. Okay, so that's 24, right? 2.4 times 10 is 24 minus 20 times sine of 37. 20 sine of 37. Remember that your calculator has to be in degree mode when you're using degrees. Okay, so this is actually 12. This ends up being 12. It's actually 24 minus 12, or 12 newtons. Okay, so step one, when we have a force at an angle, the normal force will not be equal to the weight. So I have to figure out what is that normal force going to be. Now that I've figured out that the normal force is 12 newtons, maybe I'll write that up here. You know what, and I might also write the weight. This is 24 newtons, that kind of goes fast. Now that I know the normal force is 12 newtons, I'm just going to go ahead and get rid of this work and move on so that we have some more space to think. So we know the normal force is 12 newtons, so what? Why do we care about that? Well, the problem is asking for the acceleration of the box. And I'm not going to be able to find the acceleration of the box unless I know what friction is. And remember, friction is fun. Mu times the normal force. In this case, we're calling it kinetic friction, so we put the little k's on. Well, now I know what the normal force is. It's 12 newtons, and therefore I can find what the force of friction will be. It's 0.4, the coefficient of friction, times the normal force, 12 newtons, and 0.4 times 12 is 4.8. Oh, sorry. Yeah, 4.8. So that's the force of friction, 4.8 newtons. And if I want, maybe I'll go to my free body diagram and write that, 4.8 newtons. Okay, great. So why did I want to find the force of friction? Okay. Acceleration. We find acceleration by taking the net force and dividing by the mass. Now, in this problem, the net force in the y direction was 0, meaning all of the up and down arrows, they're balanced. They add up to 0. But the x forces, the left to right arrows, they're not necessarily balanced. So that means that my net force is in the x direction, and it's going to be whatever the right forces minus the left forces will be equal to. So let's write that down. And maybe, remember, we're trying to find the net force. We know the mass is 2.4 kilograms. So how do we find the net force? That's what we're talking about. We take F cosine theta, the right force, and we subtract friction. Well, I know these values. I know that F is 20 newtons, and then I do cosine of 37 degrees, and I just calculated friction. It's 4.8 newtons. So 20 cosine of 37 is about 16 minus 4.8, and this gives me 11.17. We'll call this 11.2 newtons. So that's the net force. And this came from, again, the right force minus the left force, because these x forces, they're unbalanced. So now I put this net force and up into my equation and divide by the mass to get the acceleration. So 11.2 newtons divided by 2.4 kilograms is going to give me the acceleration, which is 4.6 repeating meters per second squared. And we did it. That's the acceleration. Now, notice that this is a pretty complicated problem. We've basically used everything that we've learned about force in this one problem. So it's okay if it takes you a little bit of time to go through it, and you have to kind of think through the different steps. The key is drawing a free body diagram. And knowing that you're supposed to take this angled force and turn it into an x and a y. Then you look at how does it compare to the other y forces and the x forces. Okay, now let's do a problem where there is a box with a force being pushed not above the horizontal, but below the horizontal. So this would be like if you were pushing down on something on your desk and moving it forward. Let's read it. A box of mass m equals 2 kilograms is pushed across a rough surface by a force of 20 newtons at an angle of 53 degrees, below the horizontal. The coefficient of kinetic friction is 0.4. What is the acceleration of the box? Okay, so first of all, let's write down the info, right? 2 kilograms, 20 newtons, what's that? That's the applied force, F. The angle is 53 degrees, and that's below the horizontal. So you just have to make sure, if there wasn't a picture drawn, you would know that the angle is below a line that's horizontal. If you forget what horizontal means, just think about the horizon. It's flat, left to right. And then the coefficient of kinetic friction, mu k, is 0.4. And what is the acceleration of the box? It wants us to find the acceleration. Okay, so again, we didn't really say this at the beginning of the last problem, but whenever you are asked to find the acceleration and you don't know anything about like the initial velocity, the time it takes, how far it goes, then that means right away you're looking for the net force and you want to divide it by the mass. So that's how we're going to find the acceleration. We need to find the net force and divide it by the mass. And finding the net force means I should draw a free body diagram. So let's do that. Let's draw a free body diagram on a dot, not on the picture so it's not confusing. And notice that when I draw my applied force, I'm not going to draw it pointing at the object like this. Instead, I'm going to draw it pointing away from the object. Because when we draw free body diagrams, the vectors, they always point away. Okay, then it's at this angle theta, and right away I'm going to turn this into a right or x component, and then a y or down component. F sine theta. Okay, cool. Then I think about, well, what are the other forces acting on the box? There's going to be a weight force down, mg. There's going to be friction back, F, K. And of course, there's going to be some normal force. Now let's stop and think about the normal force here for a second. In the last problem, the force was going up. And so that meant when we wrote our equation for the normal force, we wrote n plus F sine theta, because it goes up, equals mg. Well, now that sine component isn't going up, it's going down. Sorry, it's going down. So the normal force is actually going to be equal to n minus F sine theta. Or you know what, let's not jump, let's go back. The normal force is going to go up still, but now it has to support the weight and the F sine theta that's going down. So both of those things. Because think about it, if you push against the table, then the normal force is increasing because it has to support more and more force. So how do I write an equation for this? Well, the normal force is up, and it is going to be balanced by the downward forces. So now I'd write N equals mg plus F sine theta. And I don't actually have to rearrange anything to solve for this normal force. I just can solve for the normal force. And let's go ahead and do that just to make things a little bit simpler. The weight is mg, so 2 kilograms times 10 meters per second squared, plus F is 20 newtons. And now we're using sine of 53 degrees. So 20, 2 times 10 is 20, plus 20 sine of 53. 20 sine of 53 is 16, so we'll say 36. Yeah, that's great. We'll round it to that. You can say 0.0 if you want. Newtons. Okay, so now I know the normal force is 36 newtons. Now, notice that that's not the weight, right? The weight, mg, is 20 newtons. So the normal force, again, you're pushing down into the box, which means the table has to support more force because you're pushing it into the table, or maybe this is the ground or something like that. Okay, so why did I want to find the normal force? Well, again, because I need to know what the value of friction is if I want to find the net force to get the acceleration. So now that we've found the normal force, let's move on to friction. How do I find friction? Well, this part is fun. Friction equals mu times normal force. Okay, I know. And again, K. Good job. So 0.4 is my coefficient of friction. I multiply that, by the normal force, which I calculated as 36. Again, not 20. We're not using mg now. So, see, I used mg. What was I thinking? 36. The normal force is now 36. And 0.4 times 36 is going to give me, oh gosh, what's 40% of 36? Jeez, 14.4. I'm using a calculator, can you tell? So now I know the force of friction is 14.4 newtons. And maybe I'll write that up there. You know what? We've got plenty of room left. Okay. All right, so we found the force of friction. Why did we find the force of friction? Again, we're looking for the acceleration, which means we need the net force, which means I need to know what friction is, and F cosine theta. Because the unbalanced forces in this problem, sigma F, the sum of the unbalanced forces, they're all in the x direction. And I would take the right facing force, F cosine theta, then subtract friction. And I can figure out how much I have. I've got F cosine theta, that's 20 newtons times cosine of 53 degrees. Yep, and then I just found friction to be 14.4 newtons. So 20 cosine of 53 is 12 minus 14.4, which is actually negative 2.1. So the net force is negative 2.1. What does that mean? Well, that actually means that friction, being 14 newtons, is bigger than F cosine theta. So as you're pushing against the block, the acceleration is actually backwards. Friction is bigger than your push, which just means that the box is going to slow down. So when I use my acceleration equation, net force over mass, I'm going to use negative 2.1 newtons, divide that by 2 kilograms, and I'm going to get negative 1. 0.05, we'll say negative 1.1 meters per second squared, which is an acceptable answer. That negative just means that the acceleration is to the left. So this box is probably moving to the right across the table, but friction is greater than the forward part of your push. So even though you're trying to push it forward, the ground is too rough and it's actually slowing down to a stop. Okay, great. Let's do one last example. A box of mass m equals 5 kilograms is pulled with a constant velocity across a rough surface by an applied force of 10 newtons at an angle of 37 degrees above the horizontal as shown below. What is the kinetic coefficient of friction? Okay, well, I've got m equals 5 kilograms. I've got the applied force of 10 newtons. The angle is 37 degrees. And it wants me to find the coefficient of friction, not the acceleration. This is different. What do? Well, let's start with the free body diagram. We have the force angled up, right? So I'm going to go ahead and immediately turn that into F cosine theta and F sine theta. Okay, then I've got the weight down, mg. The normal force is going to be up. And right now I would pause and think, what about friction? Well, it's moving with a constant velocity. So that means that friction has to go back to the left. And we'll talk about that constant velocity part in just a second. Let's call that Fk. All right. So let's talk about the normal force first. I know that the y forces are balanced, so the up forces, n plus F sine theta, will be equal to the down forces, mg. Can I use that to find the normal force? Yeah, the normal force is going to be mg minus F sine theta. Okay, great. Now, before I put a number to that, let's go ahead. Wait, I guess I can't, right? Because I'm not going to be able to find the force of friction using mu k. So, okay, so let's move on for a second. Let's leave this equation like it is. Okay, well, what does constant velocity mean? Constant velocity? Oh, yeah, okay. So constant velocity tells me that this F cosine theta is balanced by friction, that they add up to 0. They're equal to each other. So now I know that friction, I guess I could write it like this, F cosine theta, positive, is equal to F cosine theta. Friction is equal to F cosine theta. Well, whoop-de-frickin' do. What do I need to do with this information to find the coefficient of friction? Well, if I use this equation and rearrange it for mu, right, divide both sides by the normal force, then now I know that the coefficient of friction, mu, is equal to friction divided by the normal force. Well, I know friction is F cosine theta, right? So I could say F cosine theta is on top. And the normal force is mg minus F sine theta. So all I have to do is plug the numbers in. F is 10 newtons, cosine of 37 degrees. And then on the bottom, the weight, mg, 5 kilograms times 10 meters per second squared, minus 10 newtons for the applied force, times sine of 37 degrees. Okay, well, 10 cosine of 37 is 8. I'll put that on top. And 5 times 10 is 50, minus 10 times sine of 37 is going to give me 44. Okay, so the coefficient of friction is 8 over 44. The newtons cancel out, and this gives me 0.18. So that's how we find the coefficient of friction in this problem. Okay, so we did a lot, and this video is pretty complicated, but you are too, and so am I, and this video is done.